Hey class, so some of you have been asking about this homework question, I think it's number 6, about the garden hose, and saying that it seemed a little bit difficult to figure out what exactly was going on. Especially the equation is quite complicated, and so I wanted to kind of give you guys some hints and pointers in starting to tackle this problem. So we have a situation here, we're using a hose to fill up a kiddie pool, and we're trying to determine how changing the hose or changing different parameters is going to affect the amount of time it takes to fill up the kiddie pool. So the kiddie pool has some volume that's probably a fixed volume. I'm just going to put V for the volume of the kiddie pool, and we're told it takes 15 minutes with this 30-meter long hose that has a 3-centimeter opening. Alright, so let's think back to the equation we learned in class. So the equation we learned in class for flow rate is flow rate Q is equal to all this crazy stuff. Pi, that's a Greek letter pi. Let me rewrite that because that's ugly. Okay, we got pi, we got the change in pressure between the two ends of your hose or whatever the object is, multiplied by the diameter to the 4th power, and then divided by 128 times nu, right, which is the viscosity, and multiplied by the length. So that looks good, but in here we have Q, which is flow rate. We're not told anything about time or volume. But what is flow rate? Well, flow rate is the rate at which things flow, so that's the amount of volume that fills up in a given period of time. So flow rate is really volume over time. Okay, so let's start with the first question. If you replace the hose with a longer hose, would the filling time be more, less, or the same? So there's two ways to answer this. One is just to think logically. A longer hose means more energy is going to be lost. Probably it's going to take longer because you're losing more energy. So my first guess would be more. Let's see if we can verify that with our equation. Here's our length. If our length increases, it's on the bottom of this side. That means the bottom of this side, the time, would also have to increase. So yes, it would be more. And that equation shows us why. Alright, part 2. Oh boy howdy, now we have to calculate something. Okay, so we're asked to calculate the amount of time it would take to fill if we had a new hose, which was longer, at 55 meters. So first of all, based on our answer to the previous one, it should take more than the 15 minutes it took originally. Okay, so let's look at how we can use this equation to determine the time, again based on the length. So if we look at our equation, maybe I'll rewrite it down here. I got volume over time equals all this stuff. Pi times the change in pressure times d to the 4th over 128 viscosity times length. So if we look at this, the volume of the kiddie pool is staying constant, 128 is staying constant, the viscosity is staying constant because it's still water, the diameter of the hose is constant, the pressure difference between the pipe and the outside is constant. So all of these things are constant. The only thing changing is the time and the length. So what I can do is I can multiply time to the other side, and what we can say is that time divided by length is constant. So we've done this a few times, right? I know some of us are still not comfortable with doing it, but it's a good trick in these types of problems. So time divided by length must be constant. Again, I moved my time, I multiplied it to the other side of the equation up here. So what we can say then is T1 over L1 is constant, so that's going to be equal to any other T over any other L. So once we have this relationship, we can now try to solve for the new amount of time it would take. So let's just make sure we identify our variables really quickly, right? So what is T1? That's the time it takes initially, 15 minutes. What is L1? That's the original length, 30 meters. What is T2? I don't know, that's what we want. What is L2? 55 meters. Okay, so we have those different variables identified. You could even write them down if you wanted to. It doesn't hurt to make note of your variables. T1 is 15 minutes. L1 is 30 meters. L2 is 55 meters. And T2 is a question mark, right? So now if we want to solve, we can solve for T2 by multiplying both sides by this L2 here. So T2 will be equal to T1 times L2 divided by L1. So you should be able to do the math there, and you should come out with a number that's greater than the 15 minutes we started with. So I'll let you guys do the math, but you should be able to solve for what T2 is and get, boom, box-worthy answer. Cool. So we got that. Now we scroll on down here. Let's look at the next one. Next question, if you replace the hose with a larger diameter, would the filling time be more or less, right? So again, we can look back at our equation that we had before here and use it to consider. And maybe let's just rewrite this equation. I'll rewrite the equation, but I want to get the time and diameter together. So I'm going to take this time here and multiply it to both sides. So let's rewrite it. I'm going to use a new color. So volume is going to be equal to pi change in pressure, diameter to the fourth, times time, divided by 128 viscosity times the length. So again, we're saying, all right, let's let a handful of these variables, maybe all of these guys, be constant if we're only concerned with diameter and time. If the diameter increases, if the diameter becomes larger, what's going to have to happen to the time? Well, if everything else is constant, if one value goes up, the other is going to have to go down. All right, so it should be less time, and you can use that equation to prove that. And if we look at part D right underneath this, well, guess what we're asked? We're asked to calculate what happens when we change the diameter of the hose. So from this equation up here, we can see everything's constant except d to the fourth times time. So if we use that, maybe I'll stick with the purple. It's a nice color. D to the fourth times time is a constant. So we can say d1 to the fourth times time 1 is going to be equal to d2 to the fourth times time 2. So again, if you want to find the new time, you can solve this and say time 2 is going to be equal to d1 to the fourth times the initial time divided by d2 to the fourth. Now I'm going to let you identify your variables d1, t1, and d2 and try to solve, but you can always use what you answered in part C to help check. Is time 2 actually smaller than time 1? If so, that's a good sign. If not, you may have done something wrong. Alright, so now moving on to the next part, it's really the same process. Alright, we're going to just keep continuing. Now though, we're given a situation where we're having a change in pressure and we want to see how that affects the time. So again, you're going to go with the same basic idea that you've been doing already. So again, I'm going to multiply, or really write the same equation we had before with time on the other side. So volume is going to be equal to pi times our change in pressure, diameter to the fourth, times time, all divided by 128, viscosity, the Greek letter nu, times the length. So again, we have a situation where everything is constant except for change in pressure and time. All the rest of these are constants, so what we can say, as we've seen before, is that your change in pressure times your time is constant now, since no other variables are changing. So for the second part, or part F, not the second part, we're going to have delta P1 times T1 equals delta P2 times T2, right? And you can solve that like you've done on the other ones. I'm not going to go any further than that. I'm going to trust your guys' ability. And so then, for answering part E, consider delta P times T. If one changes, how does it affect the other? That will help you answer part E, which I also will not answer for you at this time. So, try that out. If you have additional questions, let me know. Otherwise, have yourselves...
Trust the process.
Yeah, trust the process.
Trust the process.
And have yourselves a box-worthy day.